Good morning. We are all very quite used and accustomed to energy performance limits for products. So energy limits and energy efficiency at product level. But it is also possible to get something more, some more energy efficiency if we accept and start a system level approach. And this is the topic of the presentation. First of all, we do a very quick step back to the product level energy efficiency, recalling the concept of the European Union eco-design. The eco-design is a set of product level, technology neutral, energy saving and ecological requirements for a wide range of products that translate mainly in minimum efficiency levels for products like washing machines or professional refrigeration facilities and equipment, better insulation of buildings, energy recovery in running systems and running units, and also in some technical solutions like modulation of the duty of the devices, like using inverters and so on. The eco-design has been quite effective so far in the European Union because it has saved approximately 16% of our primary energy, or it will save 16% by 2020 compared to 2010. So acting and imposing energy efficiency levels at product level is really effective. Now, first of all, just between brackets, sorry, in order to respect the time, I will have to skip some slides, but the presentation is fully uploaded and will be available for you to download it. Now, just let me skip to this one. This is a typical outcome of the eco-design requirements, but also of other programs that you may have in the USA or China or also Australia. With a particular focus on a refrigeration cycle, you have a compressor, you have a controller that drives the compressor through an inverter, number 7 at the bottom, in order to modulate its cooling load, its cooling output according to the load, which is sensed by the sensor. And the modulation allows to do energy saving and at the same time to better maintain the set point of humidity, which is this line, if I get this is the pointer. Yeah, the red line here, the dotted line is the set point. So the modulating system is the blue line, which is more or less oscillating around the set point. Instead, if you did not have any, I've got the laser point. Sorry, I saw it. Thank you. And if you did not have the modulating system, you would have much wider oscillations due to the on-off behavior of the refrigerating cycle. Now, stability and energy saving at the same time, and this is the typical result of eco-design systems. Apart from inverters, we introduced, you have in the market other solutions like electronic expansion valves to fully control the refrigerating cycle in order to modulate and change and adapt the superheating and the condensing pressure, or the newly introduced ejector, which exploits the energy which is still present at the outlet of a gas cooler or the dry cooler to act as a pump. And since it acts as a pump, we can reduce the energy used by the compressors to further compress the gas. Sorry, I have to go a bit quickly, but we can come back by questions on that. Another possible solution is evaporative cooling. If you exploit the natural evaporation of water into the air and from the coils, you can support the heat rejection from condensers, from dry coolers, thus reducing the load of the compressors, of the pumps, of the fans, and so you can do energy saving by a natural phenomenon. So at product level, the main conclusions are that a modulating product helps to guarantee a stability around the set point. So that's important for food preservation, process control, comfort, and so on. But it also helps to reduce the energy consumption. Is that enough? No, it is not enough, actually. According to the last IPCC report, if we want to respect a maximum increment of 1.5 degrees centigrade of the average temperature of the globe, we should do something else. Apart from changing our behavior, which is quite important in order to make all of our activities more sustainable, we should also possibly, and we will have to do that, improve the energy saving and the energy efficiency of products. Products, but also systems. We can do more, just skip to this one, if we adopt a system approach to systems of products. A building is a system composed of many parts working together. Thinking about the ventilation systems, you may have different ventilation systems supplying air to the different zones, condition zones. And we can go to this one. And all these systems can be combined, properly driven together, and also the products that compose the systems can be driven and controlled in an optimal way in order to do these savings. These savings, the ranges are reported as 16% to 49% of additional saving by the European Union, the first one, or between 23% and 49% by the PNNS report of May 2017, can be obtained if proper software for controlling the devices are implemented in order to drive them in an efficient way. So not only efficiency at product level, but also efficiency in a way that systems are controlled. Now, a system, you can see, is composed of many devices, many equipment. It can be different engine units, can be different refrigerating cycles, also pumps, and there can be energy storage systems, like we heard at the beginning of this morning. And they have to be combined and driven together in order to maximize the energy saving. Consider also that systems may have different set points. Very often we are focused on humidity and temperature. They are two important set points for many processes, but as a second set point, you can have the minimization of the running cost, which is important for the users. Third set point can be the minimization of the total primary input energy in order to minimize the CO2 generated, so the indirect emissions. Number four can be the minimization of the water used in case you have humidification and evaporative cooling systems. And yet with those you can do cooling in order to reduce the energy used by chillers for doing cooling. And a fourth one can be the maximization of the outdoor air intake if you need air changes inside the conditions environment. So systems are a bit more complicated than products because they may have different hierarchical goals, and depending on those, they have to be controlled in order to fulfill all these goals. But energy savings can be of that order of magnitude. Okay, I already said this one. And this is quite interesting. This is about, I'm going to show you now two cases. This is a case of a ventilation system using very simple one. This is an extreme case just to explain to you the meaning of controlling a system in this particular way. This is a ventilation unit with just a cooling coil doing cooling by a chiller and an evaporative cooler, DEC, spraying water. When water evaporates in the air, it does cooling at the same time and also humidification. Now, both can run at their minimum duty in order to do the minimum level of humidity, the EC, and the minimum level of cooling in order to respect both the set point of temperature and humidity. However, since the evaporative cooling can also do cooling, you can exploit the tolerance on the humidity set point in order to do a bit more humidity, but yet respecting the tolerances on the set point of humidity, and cooling at the same time, so that you can reduce the duty of the cooling coil and saving energy at the chiller. You can see it from these charts at the bottom. So the light blue bars represent the total primary energy input when both the evaporative cooler and the cooling coil are running at their minimum duties in order to guarantee the evaporative cooler, the humidity, the minimum humidity required, and the cooling coil, the minimum temperature required. If you, let's say, displace their duties and you increase the sprayed water, and so the cooling effect of the evaporative cooler, it will, yes, consume a bit more energy, from 34 kilowatt to 39, but at the same time the cooling coil will decrease its duty from 385 to 304 kilowatt, and therefore the sum will decrease from 419 to 343. Of course, you will use a bit more water, but the final result will be that while still guaranteeing the set points of humidity and temperature, you will save energy. So when you work at the system level, you have to adapt, move, change the duties of all the equipment in order to reach the final system goals. And very often you have to make the equipment, the devices, outside for their maximum efficiencies in order to maximize its efficiency at the system level. This is a different kind of a mentality and approach, but quite effective. Oh, this is a similar system. It's a bit, okay, I can skip this one because I've already explained the concept in the slide before. We've seen with the ventilation system a case when the devices interact with each other, the evaporative cooling and the cooling coil. But there are also systems where this type of bond, this type of relationship should be broken in order to make the devices independent and do a better energy saving. This is the example of a supermarket. In a supermarket, you may have a unique refrigerating system or loop serving both the low temperature cases and the medium temperature cases. They are all connected together and served by refrigeration center and remote condensers and so on. The remote condensers, the chillers, the refrigerating main equipment serve all the cases, so they have to work also for the low temperature cases, even more than what is necessary by the medium temperature cases. If you broken up this cross-influence between the display cabinets and you make them independent from each other, then you can get some additional benefits. First of all, of course, the heat will have to be rejected using a medium. That can be a water loop. So there will be some water moving across all the display cabinets, accepting a heat that they reject, and then the heat is rejected by a chiller or by using eventually free cooling or by dry cooler, something like that. But the display cabinets will become independent from each other at that point. So each one will be able to modulate its cooling capacity according to the real load. And since they are independent, you can have some energy saving in that case. Additionally, if one breaks down, only that one will break down. The others will not stop. Something more, apart from the benefits, is that in total less refrigerant can be used. All the display cabinets can be hermetically sealed, so this way you also reduce the direct emissions of refrigerants, if any. And the installation can be a bit easier because the water loop is not pressurized and you do not have a huge amount of refrigerant moving around in the supermarket. What I mean is that when you do a system, you have to consider its peculiarities. In some cases, you can exploit the bonds and the links and the relationships between the equipment that make up the system itself in order to minimize the energy saving and yet respect the set points. In other cases, it is better to break the bonds and make the system, the device is independent to get the same or similar benefits. What more? Well, okay, let's skip this one for a moment. Supervisory systems. A system can run independently and can be selfish to some extent if it's got a very good software. However, as already outlined by Mr. Sepulveda, continuous commissioning is really very beneficial. And if you have continuous monitoring you can continuously check what the system is doing. You can also interact with the system. You can do a kind of continuous fine-tuning and get additional energy saving, and also do preactive servicing to avoid the downtimes, so that you can preserve its capacity of serving the processes. Apart from these nice pictures, this is quite important. That's reported by the IEA's Energy Efficiency 2017 report. This chart show that if you have a good monitoring system or monitor energy consumption system, you can improve the energy saving by 3% or even up to, let's say, 12% if you have very good skilled and trained personnel. So energy management systems, which are kind of monitoring systems, allow to keep the systems under control, make a continuous monitoring, and do additional energy saving. Step further, the IoT, which is a fashion concept nowadays. It is slowly, little by little, coming in the market. When you have the Internet of Things, you have different devices connected together through the Internet. You can check them out. They should be hopefully plug and play. When you connect new ones, they exchange data, and by digging into the data, you can fully control the system that you are responsible of. And these are just concepts, types of IoT definitions and services. We go from what is called descriptive analytics, which means just description of what the system is doing, to preventive, understanding what might happen in the future, to prescriptive, which means that the IoT system suggests interventions, to proactive, in case it, in the future, maybe it will automatically do corrections to the systems. At this stage of the story, of our story, these are still, let's say, concepts, but they are coming, they are being created, elaborated, but the monitoring systems are very effective. This week, the government of Australia released a report called Hard Facts number 3, and in that report it is described and stated that the Coles, a supermarket chain in Australia, is doing a 24/7 monitoring of all of its stores, and they have obtained 20-25% of energy savings since they began to monitor all the stores. At the same time, they've been able to reduce the refrigerant leakages from an average of 25% per year to 6% per year. So they have been able, through monitoring systems, both to reduce the indirect emissions by reducing the energy consumption, and also the direct emissions by reducing the refrigerant leaks. As a conclusion, okay, I skip to the conclusion now. We can say that usually the efficiency of products is the first step towards reducing the energy consumption of systems. That involves better insulation, energy recovery, modulation of the duties in various forms. Second step is the efficiency of systems of products to harness more potential energy saving. I mentioned the demand side flexibility. It is described into the slides. It is mentioned there because when you do efficiency of systems, you may also include the management of demand side flexibility, in particular when you have a lot of renewables into the power grid. And then the third step consists in energy management systems, supervisory systems, and the IoT to possibly proactively improve the performances of products and systems. So, going back to the eco-design, if the eco-design can guarantee more or less 16% of primary energy saving in 2020 compared to 2010, by good and proper monitoring systems, we can increase that energy saving by 10%, up to maybe 25% statistically, and even more by energy management systems, which can be considered as a kind of first step towards the IoT. Finished. I've been quite quick, sorry. Thank you. Thank you.